Good morning, everyone. Today we are going to discuss about solar charge controller, which is an important component inside solar systems, especially in off-grid and hybrid solar systems. We have to use this solar charge controller because in off-grid and hybrid systems, we are having batteries for storing the power. We are using battery. So we always have to keep this battery without overcharging, because overcharging will be causing several problems like overheating can happen, gassing is there. Then in severe cases, it will be causing that battery to explode. Overall, it is not good for the life of the battery. It will be damaging the battery. So for preventing that, we need to use a solar charge controller. So a solar charge controller, it's actually a solar charge regulator. It's an electronic device. So it is used inside off-grid and hybrid off-grid applications. And it is used to regulate the current and voltage input from PV arrays or PV panels to the batteries and electrical loads. So since the voltage and current inputs are regulated, and only after the regulation they are given to the batteries and also to the electrical loads, that batteries are protected and also the electrical loads are protected. So what are the advantages of solar charge controllers? That overall, already I have mentioned that it is mainly used for the battery protection. So it prevents overcharging and deep discharging of the batteries. Then also it is increasing the overall system efficiency, because always it is maintaining that regulation of the voltage and current. It is increasing the overall system efficiency. Then load protection. Then reverse current protection. Reverse current protection means at the night time when the solar panels are not producing any charge or power, that is at that time battery will be storing the power. Okay, so that battery power will be flowing back to the solar panels at the night time. So that will be causing the battery to get drained. So we need to stop this. We have to prevent that. For that, inside the solar charge controller, there will be a blocking diode, or in some updated versions of solar charge controller, MOSFET, that a semiconductor device like MOSFET is also used, and it will be preventing that reverse current, that is the current flow from the battery towards the panel. Then also it is that solar charge controller will be helping us to reduce maintenance of the battery bank, because that it is always regulating that its input and also it is maintaining that without overcharging. So that maintenance of the battery bank also can be reduced. Then it can improve the battery life. So by protecting the battery, so additionally, it is improving the battery life. That is, overcharging can cause the battery to get damaged. It will be affecting or reducing the battery life. While using a solar charge controller, this problem is solved and it will be improving the battery life. Then, two important types of solar charge controllers are, first one is PWM, pulse width modulation. So using pulse width modulation technique, we can regulate the voltage and current input to the batteries. So there we are using a transistor. So inside the PWM charge controller, there will be a transistor acting like a switch. It is used to rapidly switch the connection between the solar panel and the battery on and off. And it is adjusting the width of the on pulses. We know in pulse width modulation, by changing or by adjusting the width of the pulses, let us modulate. That is, let us control the voltage. So let us modulate or adjust the voltage. Thereby, let us control the amount of power delivered to the battery. So it is suitable for small systems where panel voltage is equal to the battery voltage. That is, when the panel voltage is equal to the battery voltage, and for smaller system, this PWM, pulse width modulation techniques will be suitable. So like it is mentioned that by adjusting the width of the on pulses, let us control the amount of power delivered to the battery. So when that battery is near to its full capacity, let us, like by changing that, by adjusting the width of the pulses or by adjusting the pulse length, let us control the charging of the battery. That is, let us reduce the rate of charging of that battery. Thus, let us reduce or let us prevent the overcharging of the battery. Okay, so by controlling the width of the pulses, by pulse width modulation, we are controlling the amount of power delivered to the battery, thus preventing or protecting the battery from overcharge. And it is a less expensive system when compared to the another advanced, that is MPPT type of charge controller. It is a less expensive and simpler type of system. Then in maximum, the power point tracking, that is MPPT system. So MPPT, it is an advanced technique. So there we are using MPPT algorithm to track the optimal voltage and current. So MPPT algorithm will be like this, an algorithm is there, that is MPPT, maximum power point tracking algorithm. So always this controller is comparing that voltage and current. Always it is monitoring the voltage and current, and it is dynamically adjust their input parameters to continuously find the maximum power point on the solar panels, voltage, current curve. So for at each available voltage and curve, it will be tracking always where that maximum power is achieved. So by tracking always continuously tracking the maximum power point, so at any situation like low light situations or cloudy climate, etc., it can track that maximum power point. Continuously, it can track the maximum power point. So by that, always it will be extracting the maximum power from the PV module at its peak power point. So it delivers higher charging current compared to PWM. That is like in PWM charge controller, actually that is not, the controller is not stepping down the voltage. It is like pulling down the voltage, that adjusting the width of that pulses, input pulses, it is controlling the voltage. So suppose we are getting an excess voltage, like in excess voltage we are getting, that power is excess, like the voltage window is excess, or that voltage output that we are getting from the panels, solar panel is higher. So that excess voltage cannot be used fully in PWM controller because it cannot adjust or it cannot step down the voltage according to the battery voltage. But in MPPT, MPPT controller is able to step down that voltage. So if you are getting an excess voltage, that can be stepped down. So while stepping down the voltage, proportionately the current will be stepping up. Okay, so we will not be losing power. So like that excess voltage is actually, it is proportionately converted into excess current. So power loss will not be happening. That power loss is happening inside a PWM controller. Because there, if you are getting an excess, that PWM controller is getting an excess voltage that cannot be utilized fully. So power loss will be happening there. But in MPPT controller, that power loss is not happening. When the voltage is stepping down, proportionately, current is stepping up. So that power loss is not happening. Like when compared to PWM, power loss is not happening in MPPT controller. So always it is extracting the maximum power from the PV module at its peak power point, and it is delivering higher charging current, that is that can be fully, that excess voltage can be fully utilized by the MPPT controller to charge the battery. Then it is suitable for larger, more efficient systems. Okay. Then when we are comparing these both types of controllers like MPPT and PWM controllers, efficiency wise, MPPT is having higher efficiency, especially in varying conditions like I have mentioned, like in cloudy climates or in like low light conditions, etc. Always it will be having higher efficiency. Then PWM, lower efficiency compared to MPPT. Performance in low light again performs well in low light or shaded conditions. So a PWM controller may struggle in low light or shaded conditions. Then flexibility. It is more versatile, compatible with various setups, MPPT controller, but PWM limited compatibility, best for simpler systems. Then cost. MPPT is obviously it is costly, generally more expensive than PWM controller. PWM is typically cheaper than MPPT. Batteries, especially lead acid batteries, are sensitive to ambient temperature. So when the ambient temperature is changing, Accordingly, we have to change the voltage of the batteries. That is the charging voltage of the batteries. Like at low ambient temperature, for charging battery to its full capacity, the voltage has to be increased. And also at higher ambient temperature, for avoiding overcharging, we need to decrease the voltage. So in MPPT charge controllers, we are having temperature sensors. So it will be sensing the ambient temperature and it will be varying the voltages accordingly. The PWM controller is not having the temperature compensation, but some variations of PWM controllers are having that. But always it will not be having the temperature compensation, but MPPT controller is having that feature. So according to the ambient temperature, for preventing them for overcharging and also for maintaining the charger at lower ambient temperature, it will be adjusting the voltages accordingly. Then voltage mode. Voltage mode like MPPT controller is converting the excess input voltage into amperage, just like I have mentioned before. But in PWM, it is not stepping down. The array voltage is pulled down by adjusting that width of the pulses. It is pulled down to battery voltage. So when we are comparing both of the systems, MPPT and PWM controllers, like MPPT is having more advantages than PWM, right? But in several conditions, we have to use PWM that is better when compared to MPPT. So what are that conditions? So for small, simple solar systems, like we are having a small system, then suppose that solar system don't want to use that MPPT controller, PWM will be better. Then panel voltage equal to battery voltage. See, the panel voltage is much greater than the battery voltage. There we can use MPPT controller because that excess voltage can be converted to like excess current and it can be used to charge the battery. But in a PWM controller, it is not having that specific characteristic. So when the panel voltage is equal to battery voltage, it is suitable to use PWM. That is suitable for that condition. Then warm sunny climates, like warm sunny climates, PWM is good. Then our MPPT controller is mostly well efficiently it will be working in colder conditions and also like in cloudy conditions. Okay. Then cost sensitive projects like MPPT is MPPT is having expensive than because MPPT is expensive than PWM control. So always it is like if our budget is limited, then always it is better to go with PWM control. Then systems with low current and low power, that is for systems mostly less than 150 watt, let us use PWM control. Okay. So the overall performance of MPPT is always better than PWM. But in some conditions, some selected situations, let us use PWM. So by mostly about the cost wise and all, and based on the situations, PWM can be used for some situations. Then the most important part, that is the sizing of solar charge controllers. How can we size a solar charge controller? So for sizing a solar charge controller, we need to consider some parameters, both about the controller and also the batteries, and also we have to like pay an attention to the parameters of our solar panels. Okay. So when we are taking the specifications of a solar panel, mostly all the data sheets of the solar panels will be consisting of these parameters, like it's, see, the maximum power. It's an important parameter, maximum power. So the maximum power, so in some data sheets, it will be represented like WP, peak power. Peak power or maximum power. Here it is given as 300 watts. Then maximum voltage is given as 32.38 volt. Maximum current is given as 9.26 ampere. Then there is an open circuit voltage, VOC. It can be represented as VOC, open circuit voltage, 38.55 volt. Then short circuit current, that is ISC. In data sheet, you can see this parameter ISC. So that is short circuit current, which is given like 9.47. Okay, ampere. Okay, these are the parameters that you can see inside a solar panel specifications or in the data sheet. Okay, so when we are going to see some data sheet for a 40-watt solar panel, its specification you can see there. There is the maximum power 40 watt, then open circuit voltage again 22.2 volt, short circuit current 2.37 ampere, maximum power voltage 18.2 volt, maximum power current it is 2.2. Okay. Then for a charge controller, so from their specification, you can see their battery voltage, it is auto select. So suppose we are having a charge controller which is rated at 12 volt only. So it can be only connected with a battery with 12 volt of rated voltage. So it is automatically sensing that. So the voltage of the solar charge controller and the battery should be matching. Okay. Here you can see for the MPPT, here rated voltage like 12 bar 24 volt is given. Then rated charge current like 20 ampere. Then nominal PV power for the 12 volt, 290 watt, 24 volt, then it is given as 580 watt. Okay, so like that. Rated charging current, battery voltage and the PV power. That also has to be noted. Okay, and overall, while sizing a solar charge controller, we have to pay attention for these three parameters. First one, PV input voltage of charge controller, battery bank voltage, PV input power. PV input voltage of charge controller will be given inside the data sheet of the charge controller. So always charge controller's PV input voltage should be greater than panel's output voltage. For example, suppose you are having this value PV input voltage of charge controller as 50 volt. Okay, the output voltage from the PV panel should not exceed this 50 volt. Okay, then battery bank voltage. Battery bank voltage always should be matched with the rated voltage of solar charge controllers. Then PV input power. PV input power, that is, for example, I'm having like this parameter in a solar charge controller is given as 500 watt. So the power output from the solar panel should not exceed this value, that is the 500. Okay. Now, the equations for sizing the controller, that is for PWM controller, controller size in amperes, that is equal to P max divided by VMP into 1.25, where 1.25 is the safety factor. And here we can use another equation, that is ISC into 1.2. That is short circuit current into 1.2. Okay. So mostly we are using the second equation because while checking that maximum, that the current which is corresponding to the maximum power and also the short circuit current. So always sizing with the short circuit current will be better because always short circuit current is the highest possible value of current with the controller. So always it will be better to size with short circuit current. Somewhere like sometime or some persons can use this, they will be using this Pmax by VMP, that is that maximum power which you are getting from the data sheet of the solar panel and dividing that with the maximum power voltage. But always this value will be lesser than short circuit current. When we are comparing a data sheet, so here the maximum current is 9.26. but the short circuit current is 9.47. Okay, and also when we are comparing another data sheet, this short circuit current 2.37. Maximum power current is 2.2 ampere. Not much difference between the short circuit current and maximum power current, but for being on the safer side, always it is better to select this short circuit current for sizing the charge control, because that is the maximum possible current. Okay. Okay, so like we can use the second equation. Okay. In some applications, you can see that this equation is also used, but always it is better to use the second one. Short circuit current into 1.25. That is, we are adding 25% extra as a safety factor. That is why we are multiplying that with 1.2. Then for MPPT controller sizing, we are using the second equation. This is the maximum power divided by V charging. That is the charging voltage. Notice that we are not using that battery voltage. We are using the battery charging voltage. Okay. Battery voltage like 12 volt, 24 volt, then 48 volt, etc. are available. But each of these batteries charging voltage is different. So here we are using the charging voltage of the battery. That is, for a 12 volt battery, charging voltage will be 14.4 volt. For a 24 volt system, it will be 28.8 volt. For a 48 volt battery, it is 57.6 volt. Okay. So, like, these are the equations for sizing that solar charge controllers. For a PWM controller, it is second equation, that is short circuit current. This one also I have included, but we are using the second one, short circuit current into safety factor 1.25. See that P max is maximum power of the PV array in watts. So this we can find out from the data sheet. Okay. Then VMP is the maximum power voltage of the solar panel. That also you can find out from the data sheet of the solar panel. Okay. Then ISC is the short circuit current of the solar panel. That also you can find out from the specification of the solar panel. Then V charging, that is depending on the voltage of the battery that we are selling. Okay. Now let us do an example. See, we are having a solar system with 3 number of solar panels. Panel rating like 12 volt, 150 watt each. Panel data, open circuit voltage is 22.5. Then maximum power voltage is 18 volt. Then short circuit current 9 ampere. All these details you will be getting from the data sheet of the solar panel. Just now I have shown you. Then battery voltage is 12 volt. Controllers, PWM and MPPT. Let us do both. First, we are doing the sizing for PWM charge controller. So that, see, like while we are using that PWM charge controller, always it will be working efficiently with parallelly connected solar panels. See, this both PWM and MPPT controllers can be used for both parallelly and series connected solar panels. But PWM is mostly used with parallelly connected panels. Because when they are connected, when the solar panels are connected in series, that, voltage is added up in a series connection. In parallel connection, voltage will be the same. So, even if the voltage is added up, that added up voltages benefit cannot be used using the PWM charge controller. Its reason already I have mentioned. But in an MPPT controller, it is working efficiently with a series connected solar panel system. When a number of solar panels are seriously connected, current will be same, then voltage will be added up. Then that added up voltage benefit can be fully utilized using a MPPT controller. So PWM will be better to go with parallel connected solar panels, and MPPT controller can be effectively used with series connected solar panels. Okay. So, like we are going to connect that for matching the battery voltage here, that is the 12 volt. We are going to connect these panels, 3 number of solar panels. we are having, we are going to connect them in parallel. So in parallel connection, short circuit current is already given 9 ampere. So if we are connecting three number of panels, solar panels in the three number of solar panels parallelly, then the short circuit current will be like 9 into 3, that is 27 ampere. Okay, then we are adding a 25% safety margin, that is 27 ampere multiplying with 1.25, which is the safety factor, we are getting 33.75. Let us round up to the next standard size, that is 40 ampere 12 volt. If this a charge controller with this specification or parameters are available, let us select that. Okay. Then we are sizing MPPT charge controller. Again, we are considering that panels to be connected in series because that voltage adds up and the current remains the same in series connection. In parallel connection, voltage will be the same, current is added up. In series connection, current remains the same, voltage is added up. Okay. So for here, that maximum power voltage is given. VMP is given as 18 volt. Okay, so we are considering that voltage. Then open circuit voltage is 22.5 volt. That also is given. 22.5 volt. Okay. So the total maximum voltage is given as 3 into 18 volt, that is 54 volt. Then total open circuit voltage of the three panels, that is 3 into 22.5 volt, it is getting as 67.5 volt. Okay, then let us compare this voltage with the controller. That is, the controller, if the controller can handle this much voltage, that has to be controller with that has to be compared with the controller's parameters. So controller's parameters will be given in their specification or their data sheet. We have to compare this voltage if this can be handled with the controller. Okay. Then output current. Output current is total panel power. That is the output current. That is the needed parameter. So for that output current, total panel power divided by battery voltage. Total panel power. How much is the total panel power? See, here we are considering one panel with 150 watt. Such three panels we are having. Okay. Since we are connecting them, three panels in series connection, that power is added up, right? Okay. Anyway, either in series connection or in parallel connection, the power will be added. So here 3 into 150 watt. Each panel is having output maximum power as 150 watt. So that 150 into 3 panels we are having. So we are getting this 450 watt. Then this 450 watt divided by 14.4 volt, because the battery voltage is mentioned here as 12 volt. Okay. And the charging voltage of that 12 volt battery is included. Here I have included charging voltage of 12 volt battery, that is 14.4 volt. Okay. So when we are using that 14.4 volt, 450 total power divided by charging voltage of the battery, we are getting around 31.25 amp. We are adding 25% safety margin, that is 31.25 ampere into 1.25. We are getting around 39.06. Let us do this by calculator. So this is our 450 divided by 14.4, 31.25, then 31.25 into 1.2, 39.06. Okay. So here also we need to round up to the next standard size. So 40 ampere MPPT charge controller is available with 12 volt rated voltage. Then we can select that. So this is how we are sizing charge controller. Both the PWM charge controller and MPPT charge controller can be sized by using these equations. It is simple. Let us make a summary table. Like for PWM, we are connecting the panels in parallel connection. MPPT in series connection. Okay. Then based on PWM, like this is the equation that our calculation is based on. For PWM, ISC into number of panels. MPPT, power divided by battery charging voltage. Then safety margin 25%. At both sides we are considering 25%. So by the calculation we are getting 40 ampere. So it should not be, we can select a controller for PWM or MPPT. Then it should not be less than or equal to 40 ampere. That it should be greater than or equal to 40 ampere. Okay. That is how we are sizing the PWM and MPPT charge controllers. So a charge controller, when we are studying about a solar system, off-grid solar system and hybrid solar system, this charge controller is a very important component. At that time, we need to size the charge controller. So simply let us size this charge controller following this method.